Hello, everyone. Um, I am uh, I am Yucai. It is my first time in London, which is a very lovely city. I feel so excited to be here with you. And today, I and Yuming will share our optimization experience when migrating from the MPP database to the Spark. About us, we are from eBay's data services and solutions team, and we are Spark contributors. And our team is responsible for the enterprise data warehouse and data lake development and the framework optimization. We are migrating our data warehouse from the MPP database into the Spark. In the past, our data pipeline was consisted of 3 stages. And the stage 1, the online data were extracted from the OLTP system like Oracle, and the stage 2, the data were loaded and transformed in the MPP data warehouse. And the stage 3, the processed data were distributed to the downstream data mart. And nowadays, we are replacing the stage 2, the MPP data warehouse, into the Spark. So the data pipeline will become the Oracle, Spark, and the downstream data mart. Spark is becoming our central batch processing engine. In long term, we are building the whole analytic software stack based on Spark, which including the streaming, batch, and machine learning, a lot of cool stuff. The data warehouse we are migrating is quite big. It holds eBay's 20 years data, and including 5,000 target tables and 20,000 intermediate tables. Since the migration started, we are facing serious memory capacity challenge in the Spark cluster. As you can see, at many times, the memory usage is almost 100%. So optimize the memory usage is critical to us. Basically, we have 2 optimization objectives. The first is to increase the overall throughput. The measurement is the megabyte seconds. Megabyte seconds is an index provided by the Wang. For each application, it means the memory usage multiply the duration. So using less megabyte seconds means we have more available resource, so we can move more jobs into the Spark cluster. And also, we want to reduce the response time for the critical jobs. The measurement is the duration. To achieve above objectives, we build 2 critical features to enhance Spark. The first is adaptive execution, which is used to dynamically optimize the execution plan. And the second is the indexed bucket, which is used to optimize the data layout. Let's start from the adaptive execution. Adaptive execution is initiated by the Databricks at 2015. And in 2017, we create a new design and implementation about adaptive execution. The main contributors are from Intel and eBay. So what's the adaptive execution? In the original Spark, the user query will be translated into the execution plan by the catalyst, and then after the execution, we get the results. Okay, this model requires the execution plan to be fixed before execution. It is not very flexible. At many situations, even with the CBO, it is hard to know the behavior of data well enough to get the optimal execution plan. Okay, so in adaptive execution, the execution plan is not fixed. Firstly, the catalyst can see the catalyst will generate an initial execution plan. And then we divide this execution plan into many stages and execute it stage by stage. In each stage, the Spark engine can see the data statistics from the previous stage, so it can dynamically identify extra optimization opportunities and make an adjustment on the fly. Okay. So as you can see, during the execution, we can see the further optimized plan 1 and further optimized plan 2, and so on. So in such a way, usually we can get a better execution plan. This kind of technology is called adaptive execution in academia. And Oracle has already supported the adaptive execution in their latest products. We can do a lot of cool things with the adaptive execution. I listed some major cases here. Let's start from the first function, simplify and optimize the Spark configuration. Okay, when we dive into those top memory-intensive queries, we found that improper user configuration actually leads to many memory issues. It is not very surprised, because the migration of because the timeline of this kind of migration is usually very tight, as you can imagine. The earlier we can finish the migration, the earlier we can shut down the old system, and the more money we can save. And the tuning is actually very time-consuming. Some Spark configuration is very tricky. Even the experienced users need much time to tune. So the many configuration of the production queries are actually not good enough. Let's see some common configuration issue in the production. Okay, the shuffle partition might be the most difficult configuration to set. In this query, the shuffle partition is too big. User sets the shuffle partition to 5,000. It's actually too big because each task processes only 20 megabyte data. So Spark will have many schedule and I/O overhead. In another query, the shuffle partition is set too small. The user sets the shuffle partition to 600. We can see a lot of GC overhead, and so the tasks run slow. Query 2 has another issue. The ratio of memory to CPU is not good. Each core has 20 gigabyte memory. It is too big. It will lead to the high memory usage and low CPU usage in the data center. So in the classic MPP database, user has no need to consider the memory, the shuffle partition, and the performance is also good. So how can we improve this for the Spark cluster? I mean, less configuration and better performance. Okay, let's get a clue from the hardware spec. In eBay, we have separate storage nodes and separate computer nodes. Each computer node has 384 gigabyte memory and 64 cores. CPU is the most expensive resource. Ideally, we want to maximize the CPU utilization. So we plan to make each core use 5 gigabyte memory. Okay, so if each core has 5 gigabyte memory, how much data it can process for each task? The Spark's unified memory manager will use 6% of the memory for the query execution. So we have 3 gigabyte memory available for each core. And the shuffle data is usually sorted and compressed. The compression rate ranges from 5 times to 30 times. We suppose 15 times. And we need to consider the temporary space for the algorithm, like the radius sort. Okay, suppose 2 times. So roughly, we can use the red formula to get a number, 100 megabyte. Okay, what does it mean? It means if each core has 5 gigabyte memory, and when it processes 100 megabyte data, we can expect it. All the data are processed in the memory, and so we will have less spill and less GC. Okay, so how can we get each task process 100 megabyte data exactly? Okay, our solution is the adaptive execution. Let's see how it works. In the shuffle write, we use the big shuffle partition number to split the data into small blocks. And in the shuffle read, the adaptive execution engine knows each block size, so it can pack the small blocks into 100 megabyte. In this example, after the shuffle write, all the partitions will be less than 100 megabyte. And in the shuffle read, AE makes each task to process 100 megabyte data. It's just perfect to our problem. But there's no free lunch. If we just simply using the above algorithm, which will lead to the performance downgrade, so we add 2 important optimization. The first is to optimize the shuffle read. In the previous case, for the partition 1, 2, 3, the Spark needs 3 separate I/O to fetch and process them, but they are physically contiguous. So with our optimization, Spark only needs 1 I/O. We can see 1.3 times performance improvement. And the second optimization is about the map output statistics computation. Previously, it is computed by the single thread at the driver side. But when we use the big shuffle partition number, it will have obvious delay. So we introduce a multi-thread way to compute. It greatly helps solve this issue. Okay, so put them together, we can get a unified configuration solution. Here, the point is we make each core has 5 GB memory and process 100 MB data, so we can expect less GC, less speed, less schedule overhead, and very important, less human configuration. Okay, let's revisit the previous case. In query 1, the AE starts less executors and less tasks for those small stages. It greatly helps save memory. We see 1.7 times memory megabyte seconds improvement. And in the query 2, enable AE, no GC issue anymore. And we can see 1.4 times megabyte seconds improvement. And actually, we use less memory with better performance. So the overall megabyte seconds improvement is 6 times in this case. Okay, the second key function is to optimize the join strategy. As we know, there are 2 typical joins in Spark, broadcast join and sort merge join. Broadcast join has no shuffle and sort. It usually runs faster than the sort merge join, but it requires one side of the table is small. Most of the time, Spark can identify the small table and plan the broadcast join accordingly. However, for some complex queries, the Spark cannot well estimate the intermediate table size, so it may choose the sort merge join when the broadcast join should be used. AE always knows the exact intermediate table size, so it can always choose the best join plan. Okay, to achieve that, the main work includes the first, we need to enable the state estimation for the physical plan. It is similar to the CBO's estimation solution, but the CBO does the estimation in the logic plan. We need to do it for the physical plan. And also, we need to allow the shuffle readers to fetch data, to request data from just one mapper. And finally, if one table is detected as small, the AE can change the plan at runtime. Okay, so some cases could really benefit a lot from this feature. In this case, the right side table is quite small, only 13 megabytes, but the sort merge join is still used mistakenly. In AE, we know it is a small table at runtime, so we can transform it to the broadcast join correctly. And we can see some stages run much faster, from 5 minutes to 20 seconds. And the overall megabyte seconds improvement is 4 times. Okay, another key function of the adaptive execution is to handle the data scale. Data scale is a common issue. It means some partitions' data are extremely larger than others, so this task will run much slower, which dragging the whole query performance. Data scale is difficult to handle because it is quite hard to detect at runtime. AE knows the runtime partition size, so it can detect the data scale easily during the execution. And then the AE can dynamically increase the parallelism for the scaled task. And suppose table A and table B will do an inner join, and the partition X is a scaled partition. Okay, without adaptive execution, the data in this partition of both table A and table B will be shuffled into one single task. As you can imagine, this task will become one of the slowest tasks, and to slow down the whole query performance. In the adaptive execution, once we detect the scaled partition, we can use n tasks to process that partition, and each task processes a part of that partition's data. So we can make the scaled partition run faster. Okay, in this case, the AE actually launches 5 tasks for the scaled partition, and we can see 1.6 times runtime improvement on the runtime. Okay, and actually eBay uses the bucket table a lot. And when AE meets the bucket, some extra thing need to consider. The first is about the bucket table read. Because we use the big shuffle partition number, and it is often larger than the bucket number. In the current Spark, it will lead to the extra shuffle on the bucket table. So we should avoid this shuffle for the bucket table. And also, we need to add extra support for the bucket table write. In the last stage, the AE's partition is probably different from the bucket number. It will lead to many small files, so we should make the AE respect the bucket number. Okay, so overall, how much benefit we can get from the adaptive execution? We did the benchmark using the production queries, and we selected 40 production queries and run them with the adaptive execution. Our main metrics is the megabyte seconds, and lower megabyte seconds means lower memory consumption. Lower is better. On average, these queries get improved about 3 times. And the 31% of the query improved over 200%, and 83% of queries improved over 50%. As you can see, on the right table, many queries get improved a lot. Okay, that's all about our first optimization, adaptive execution. Next, my colleague Yuming will share with you our work on the indexed bucket. Okay.
In this section, I'm going to talk about indexed bucket. Actually, it's an optimized data layout. At eBay, we have some huge table. We need efficient merge and efficient filter of specific columns. For merge, bucket is the best choice as it can avoid shuffle. But downstream queries will not be very efficiently, as it will always for table scan. For downstream queries, partition is the best choice, as it can filter out a lot of data. In this case, we must shuffle the data of the huge table when merged. It's very expensive. Can we use bucket and the indexed? Can we use bucket and bucket and partition together to get advantage of both? Actually not. Spark jobs will generate too many small files. In our case, it even generates up to millions of small files. This is very bad for name node. To solve this challenge, we introduced a new data layout named indexed bucket. In order to understand what is indexed bucket and how it works, let me give an example table. DW listing item is eBay's product table. It has 2 important columns. One is item ID, its primary key. Another one is action and date. Our downstream queries usually use action and date to filter data and use item ID to do the join with other tables. We bucket it by item ID and sort it by action and date when we create this table. So in each bucket file, data is sorted by action and date with Parquet's min-max index. That's why we named it indexed bucket. So when we filter on action and date column, Parquet predict pushdown can skip a lot of row groups. That is indexed bucket. In order to support indexed bucket, we enhance the Parquet predict pushdown and add a new feature to bucket join. We add date type, decimal type, timestamp type, byte type, and short type to support Parquet predict pushdown. This enhancement can get great improvement and already accepted by community. Here is an example of Parquet predict pushdown on indexed bucket table. We want to select April 19th data from item table. We know that action and date is date type. If the date type spot predict pushdown, it only takes 10.6 hours to read 580 gigabytes. If it does not spot predict pushdown, it should take 260 hours to read 90.5 terabytes of data. Totally, this query gets improvement about 25 times. Then let's look at the feature we added to Bucket Join. To understand what we did, let me give an example query. For this circle, DW listing item join two other tables by item ID, action and date as 2 more columns. As mentioned before, item ID is bucket column, action item is sort column, as 2 other columns are normal columns. Let's take a look at the current physical plan. There is an exchange on table DW listing item. It's very expensive. Can we avoid this exchange? The answer is yes. We enhance the bucket join to avoid shuffle when join keys are a superset of bucket keys. After completing those enhancements, let's take a look at the comprehensive case. This is our production query. We want to filter April 19th data from item table and join it with 2 other tables. The join key is item ID, action and date as 2 other columns. By using index bucket, data read is reduced to 1% from almost 750 gigabytes to 9 gigabytes. As we can see, the above one has 2 stages. The one is actually a shuffle stage. With index bucket, we can avoid this shuffle. Totally, this query gets improvement about 3 times. As we discussed before, this is a big performance improvement for downstream queries. So what is the impact on the merge step? We use a full auto join to join the incremental data through item ID to merge. As mentioned before, we know that DW listing item already backed by item ID, so this huge table will not do shuffle. Let's compare the execution plan. This table with the index bucket feature has one additional sort, but this step is negligible for overall performance. From the previous case, we can see that the index bucket brings significantly benefits, reduce execution time, and improve memory efficiency, especially useful for downstream queries to avoid full table scan on big and hot tables. Now let's Yucai to talk about what we did more.
Okay, more than AE and IB. Okay, both of AE and IB are not completely in the master yet. To make them onboard the real production environment, more things needed to consider. The first is thoughtful integration tests. During our development, we created 2 test suites. One is TPCDS 100 terabyte benchmark. It is a standard benchmark, but not exactly the same as the real data warehouse jobs, because most of them are actually just the select query. And so we built another suite, which includes real eBay production queries. Now it contains about 100 queries. And the second thing is about a low-in upgrade. Okay, in our experiment, the upgrade of open source software could be more risky than the vendor software. It is understandable. Vendor can control the whole system, including the storage and the compute. But the open source software, like the Spark, is just the compute engine. So some storage side change, like the Predicate, might be unknown to it. So it will introduce more uncertainty. We highly recommend use the low-in upgrade way. It means you can enable features or upgrade certain version for just a part of the jobs instead of all at a time. If they run well, we can gradually enable more until all. And also, some stability issue you could never find in the just integration tests. And about the auto data quality check. Data quality is very important. we can never ignore the importance of the data quality. Ideally, it should happen in both integration test and the rolling upgrade. And data quality is kind of a challenge also because if you have do the data quality before, you should know some query, even you run twice, you will get the different results. It's a challenging topic. And also, at last, I listed some important implementation you might want to pay attention when you do the migration task like us. The first is about the case-insensitive field resolution. Okay, if the Hive metastore schema and the package schema are in different letter case, for example, you use the lower case in the package field and use the uppercase in the Hive's column, you will face a lot of data quality issue. And we have fixed for the package and ORC. They are in master already. And also, I listed some critical issues we met during our development. The first is interesting. When you set the shuffle partition to 8192, you will see the performance become very bad. It is because there is a hash conflict in the shuffle data and the aggregate buffer. And we have solved this issue. And another two driller is also important. They both are the block issue in the 2.3.2. Okay, so that's all for our today's sharing. Okay.
All right, thank you. We have time for a couple questions.
The adaptive execution which you talked about, is it available for the open source Spark or is it not? I mean, what's the status?
Some of feature we have open sourced, and the more feature about the adaptive execution, we will work with the community to open source them in the Spark 3.0. Yeah, it is have discussed in the Spark dev mail list, and the committer think we can consider review because the A is a very big feature, and they want to review this feature in 3.0.
Some of the features are available in which version of Spark?
In current Spark, but let me check. This feature is in discussion and is in review, and we are reaching the Databricks developers, and they told us they would like to review with us in the 3.0, and these two features, the second one has been merged, but the previous one is still in reviewing. Okay, and actually we have more features about adaptive execution. For example, all these drillers are not submitted to the community yet. And our friend from Intel will do another deep dive about adaptive execution. If you are interested, you can check their session also.
So you mentioned the adaptive execution helping with skewed data for joins.
Yes.
I'm interested to know, is that also going to be implemented for co-groups as well, or only for regular joins?
Excuse me, for what?
Co-grouping. So when you co-group two sets of data together, so a data set operation? It's similar to a join, but it's not
yes,
a join.
The skewed we did for the skewed join, only did for the skewed join.
Okay. Thank you.
All right, thank you, and please be sure to rate the talks afterwards. Thanks.
Okay, thank you.